Hello, I'm Brian Bailey, Technical Editor for Semiconductor Engineering. I'm speaking with David Abercrombie, Program Manager for the Advanced Physical Verification Methodology at Mentor Graphics. We're talking about the differences between double and triple patterning. David, can you first give us a reminder about double patterning and some of the major differences between the two?
So, I think there's two basic differences I'd like to focus on comparing double patterning to triple and quadruple. Triple and quadruple, I'll say, are very similar to each other. There's not any fundamental changes going from 3 to 4, but there's fundamental changes going from 2 to 3. And there's two basic fundamental changes that affect the designer in the end. The first one is not inherently evident on the surface just by looking at it, but I wanted to kind of demonstrate it with some drawings here. And it has to do with, algorithmically, from a computer science standpoint, how you would actually automate the process of determining the coloring of a layout in 3 colors versus 2 colors. Or, in parallel, determine whether the coloring is illegal or not, whether a coloring exists, a legal coloring exists. So let's start with double patterning. And in these pictures, I'm drawing what we refer to as a graph, but these round circles would represent shapes you draw on a layout, and these connections between them would represent the spacings between those shapes on the layout that require them to be a different color. You know, but it's still, the fundamental requirements still hold. In any multi-patterning process, if things are far enough away from each other, two shapes, they're okay to be on the same mask. They're printable. If they get too close, they can no longer be on the same mask. They have to be on different masks. So we refer to that when any two shapes are close enough that they were now required to be on different masks, we say they have a separation requirement, that they have to be separated on the two masks. And we represent that as a line here saying that there's a separation requirement between these two shapes on the layout. Now in the graph world, these nodes have no physical location, they're just points of reference. But they represent things they represent shapes on the layout that have spacing requirements that require them to be different nodes. Now, if we look at double patterning, how would I determine a coloring? You know, how do I color these shapes? If we look at the problem, thinking about it algorithmically, if I were to start here, the first question becomes, well, what color should that be? Well, I have two choices, right? Color 1 or color 2, and I've got 2 markers. We'll choose red and green, okay? So let's say I decide to make it red. That was a choice of 2. But given it's double patterning, when I go to the next shape that's connected, what color does it have to be? There is no choice, because there's only 2, and I've already used one. Okay, so the choice of the second one is made essentially for me. There's no choice to make. Similarly here, this one has to be color 2. And now that I've made that choice, the next one, the choice is made. I don't have to decide or guess or anything. It's got to be 1. In that case, that works for both of them. If I go here, I know what the answer is. It's 2. If I know that, I know this has to be 1, and that has to be 1. Now, in this particular graph representing a layout, that's not legal, because there's a separation requirement. These need to be different colors. One of these needs to be 2, and one of them 1. So the question immediately becomes, if I've got to here, is the answer actually that this is not colorable? Could I have gone back and made a different choice that would have changed this outcome? Now, you could argue, well, I could have chosen 2 here. This was the only choice I actually ever had. Okay, so I could have chosen 2. That would have made these 1, 2, 1, 2. But it wouldn't have solved the problem. So the good thing about DP is there's no point at which you get to some place where the coloring is wrong or not viable, and I have to second guess that if I'd have only done something differently, maybe it would have worked. No, there was nothing I could have done. So from an EDA software perspective or an algorithm perspective, the runtime that I can expect from a tool that's going to determine a coloring is basically correlated to how many round circles there are in this picture. The more circles I have, the more operation I'm going to have to do to color them and decide whether that's legal or not. But I never have to, at some point, decide, maybe I'll go back and try something else. It just, however big it is, it's how long it takes to do it. Okay?
So that was double patterning. Now, David, what's the difference between that and triple patterning, and how would that play out on one of these graphs?
Okay. Now, again, I want to determine a coloring. When I get to the first, start arbitrarily in some point, I'll start here. Immediately, the problem's a little harder than before, because now I have 3 choices. Here I only had 2 choices, either 1 or 2. Now I could choose 1, 2, or 3. And let's say I arbitrarily choose 1. Okay? But that's not much more difficult than that was. But now when I get to here, what color should it be? Here there was no choice. I knew exactly what it had to be. Now there's a choice. It could be 2 or it could be 3. Which should it be? I don't know which it should be. So let's say I decide to make a 2. And from here I make have the same decision. What color should it be? I don't know. So let's say I choose 2. Is that okay? No. I then find out, having made this decision, that that's not legal. So what do I do about it? Do I go back and change this to some other color? Should this have been 3? Would that work out or not? Or should this choice have been different? Should this have been 2? Or should this have been 3? You see, there's many possible things I could have done. I got a 1, 2, 3, 1, 2, 3, 1, 2, 3. There's all kinds of possible ways I could have done it. In this particular case, I at least had to change one of my choices, and I could resolve this. I did that one too. I got here, determined that was wrong. Okay, there was a choice I could have made, so I could change that one choice. Okay, I got it. I think I got it fixed. Okay, so we go here. Now, what color should that be? I don't know. It can't be 2, so I'll make it 3. Again here, what color should that be? I don't know. I'll decide to make it 1 again. Okay. Let's say this came on around. I make this 2. I make this 1. No, let's say I make this, like it here. What color should this be? Okay, let's say I make it 3. If I have no reason to pick one over the other, I pick 3. Okay. Well, if this is 1, this can't be 1. Okay. Well, this one's 3. Can't be 3, right? It's got to be 2. Same thing holds here. It's got to be 2. Okay. Well, that's not legal. So what do? I got to go back and change something. So what could this have been 1? If I go back and make that change, that would actually work. But remember, these were arbitrary too. What if I had by chance chosen that to be 1? Now I'd come back in here and say, well, it couldn't be 3, and now it can't be 1. But I go, oh, but I could have changed that to 2. So I might have to come all the way back here and make a change here to make this work. The worst case scenario, theoretically, is that I could get all the way to the end of this, find out it doesn't work, and have to go back and start all the way from the beginning and try a completely different set of colors. Okay? The actual true worst case is that I make such bad choices along the way by accident that I end up trying every possible choice of coloring until I find, by luck, finally the right one. Okay? So, how long will it take to run this? It depends. If I'm lucky and I choose well along the way, I might solve it like that. The first time through. In this case, I made at least 2 wrong choices along the way. They had to go back and change, which increased the runtime. Okay? If I made 100 wrong choices along the way and had to go change all 100 of them 3 times, the runtime would get longer and longer and longer. So there's a potential that the runtime of this could explode and become very, very long.
What can be done to constrain the complexity and make it more likely that a solution can be found?
So the typical approach to solving those solutions is to somehow try to constrain the problem. You can't have an open-ended problem. You just can't say, I'm going to draw any possible thing and try to always find a solution on any possible thing, because it's proven to be this NP-hard problem, this non-practical problem to solve. So that was a big challenge. I mean, we're the software people saying, hey, this is not doable. There's no such software solution that we can give you that's going to give you practical runtime. And we know if it won't run overnight, you're not going to buy our tool. And 10-year runtime is not a good marketing strategy. So we had to work on some way to simplify the problem and make some practical solution. And that's where the real interaction with the foundries came in, and a lot of work trying to come up with a solution. And we basically took a two-step approach to solve the problem. The first trick, if you want to call it a trick, software approach to making it better, is something we call graph reduction. And that's looking at the graph that you've created by drawing your layout and seeing if there's a way to simplify it. And there are a lot of ways that exist. Just an example, looking at this particular shape, this particular combination of 3 things here. This particular one interacts with these 2. Okay? So we call this a degree 2 node. It has 2 degrees of requirement attached to it. So basically, because of that, it has no other requirements associated with it. Because of that limited set of requirements impacting upon it, if I know these 2 colors, this color is easy. I know that I can find this color. Whatever these are, because there's only 2 and I have 3 colors, I know I have 3 colors. Regardless of what these come out to be, because of everything else, I know I can find the answer to that one. I know a color exists for that, and I'll know what it needs to be. Okay? So I can basically pretend it's not there. I can solve this graph. When I figure out what these need to be, I'll just go stick that back in, because I know that's solvable and it's trivial. Okay, so now I can simplify the problem, and you can see real quickly. Well, now that I eliminated that, this now only has 2, and it becomes the same scenario. I can pretend that's not there. This one only has 1. I know whatever this is, I can figure out a solution to that one, so I can trim that one, trim that one, trim that one. These are both degree 2. Those are degree 1. That completely goes away. Okay. There are tricks to make pretty complex graphs reduce very quickly to very trivial problems. And that's trick 1, is to reduce the graph to much simpler things that even if you had to apply a complicated algorithm to it, it's doable in runtime. Basically, that it might surprise you that went away completely, but basically there were so few nodes on that graph that those decisions are going to be, the trial and error is going to go fast enough to make that solvable. The problem is, how do we guarantee that everything you draw is going to reduce to something very simple like this? If everything did reduce to something simple, this problem would be solvable. But how do we guarantee that? And that's where the second layer of solving this problem came up. We have to constrain what you draw to in some way that you never create a complicated enough set of polygons with their interactions. If you got polygons interacting with all kind of other polygons, very complicated constructs in huge numbers that maybe all these reduction techniques don't whittle down to something trivial. We got to protect and make sure you never draw something that's going to be so complex that even after reduction, now we're stuck again. Does that make sense? And that's been the most complicated thing to work out with the foundries. How do we constrain what you draw? Because that's the one word designers hate. Constrain.
I presume we're talking design rules here.
Design rules here, yes. And think of it like, it's really a combination of design rules and methodology. You know, if you look at particular types of layout like a standard cell, you got a power rail and some shapes in between the power rail. It's a nice thing about standard cell design is it kind of limits the complexity of the graph. Everything in here, you got a next set of standard cells up here. It's always, this set of stuff is always isolated from this set of stuff by this one big node. You know, this might have spacing interactions to all these, and these have spacing interactions to each other, but they all touch this one point and then branch back out again. So if you were to draw a picture of it, you'll see all these pieces of polygon inside the standard cell interacting. They all interact with the power rail, and then the next set of shapes interact within the next one, and then they all interact with the power rail. So particular design methodologies will always, this ends up breaking into nice, simple problems. I can solve the problem in between and then just connect them at this point. So a good design methodology will limit how complex this gets. But of course everything's not standard cell design. There's all kinds of design. So that's really one thing that we did. We worked with the foundries. We came up with those graph reduction techniques. They would draw sample layouts. They would try, well, what if we make the cells look like this? Or what if we do an SRAM like this? You know, they would say, here's how we were thinking about drawing them. They would run our tool on it, and we would try to reduce the graphs and show them, here's how they reduced. These reduced great, but maybe this one didn't. It was still too complicated. We point that out, and they'd go say, well, maybe if I don't allow A, B, or C, and they change a design rule or an approach to doing the cell, we'd rerun it. And we iterate and iterate and iterate until they came up with a pretty good set of design rules, a pretty good methodology, where everything reduced nice and well, and no problem ever got out of hand. Does that make sense pretty much? So it was pretty successful. The challenge, though, is if you think about like what Calibre really is, it's a verification tool. It's a checking tool, right? What are we checking against? We're checking against the case where you don't follow the rules. That's the point of the tool. If you always follow the rules, you never need to buy Calibre, because you never break a rule. There'd be no rule to flag. There'd be no error to flag. The whole point of Calibre is to catch the case where you did not do what the design rules told you to do or the methodology told you to do. That's why you buy the tool. So despite having worked out a great approach with the foundries to say, if you'll follow these design rules and you'll follow these design methodologies, this problem will never get out of hand, and we'll always be able to color it, or at least tell you it's not colorable, and have a practical, reasonable runtime solution.
Thank you, David, and thanks for watching, and I hope that's answered a few of your questions about the differences between double and triple patterning.